you're suddenly out of... Oh, pick where you're gonna sit.
I'm sitting right here.
Okay.
I've always been here.
You actually leaned forward and worried me for a moment. There. We are live.
Excellent.
So how is life in Canada?
Good. We've got all kinds of wildlife just exploding all around us. I saw white-crowned sparrows back for the first time. There's a flicker who's on the top of a tree, and he's just
flicker?
yelling and yelling and yelling. A flicker? It's like a kind of woodpecker.
Okay.
Yeah, you must have them there. They're really pretty, but they're like a fairly big woodpecker. We've got deer in the garden again. So that is always my challenge, my battle, my fight. Although it's funny, so we have deer, and it's like bulb season right now, where so all of the tulips and all of the daffodils and all of the snowdrops and hyacinth, these are all coming up.
Yeah.
And the deer got into the garden, and he ate the first thing that he could find, which were garlic. Oh. And didn't like it. So munched a bunch of garlic, decided that they're not his thing, but has then avoided all of my other bulb-based plants.
That's
and
awesome.
So, yeah. So all of these tulips, they're goners. Like, they're all just screwed. Nope. Everything is, the daffodils are coming up. The tulips are coming up. It's going to be beautiful. And the deer just doesn't want any part of that. So I think so I should have a nice, good spread of flowers in the garden this year, which is going to be great. The trees, though, that's my challenge. It's the fruit trees that the deer just demolish.
Yeah.
And it can be a death blow to a tree. Like a young tree, first year, putting out its leaves, deer comes in, eats it, kills off all its leaves. It tries to bring back its leaves later on in the season. Maybe another grazing happens. I've mentioned this many times.
Yeah.
Deer don't enjoy the leaves of trees. They feed on sadness. And so they'll eat whatever makes you the happiest.
That feels very accurate.
Yeah, they're monsters. They don't care as long as they can, they're out there with their little glowing eyes watching as you cry. Like the emotional vampire in What We Do in the Shadows.
We have currently the strangest looking backyard because I let my chives go to seed. And so chive seeds blew all over our back lawn, which is not the healthiest of lawns because we have moles in huge numbers.
Now it's about to be a chive lawn.
And the chives grow so much faster than the grass. And so our backyard has all these like really tall clumps of chives all over it.
I hope you use them for cooking.
Yes. Well, not the ones that are in the lawn because they're in dog territory. But
right, of course.
We have a big pot of chives that produces more chives than we can use. But currently the backyard looks really bizarre. And there's also basil that grows in the backyard because I let the basil go to seed. I may do this on purpose. But this means that when someone mows our backyard, it ends up smelling like the weirdest Italian salad ever.
Chives and basil, some kind of spicy pesto. That sounds great.
Yeah.
All right.
It's fabulous.
Let us do our job.
Okay. Oh, shoot. I forgot to open Audition. Sentences I say almost weekly. And yet I will never learn.
No, you never shall.
18 years. We've been doing this for 18 years.
So maybe on our 36th year.
Yeah, so this is episode 750, and this morning I found myself doing I wonder just how many episodes we will end up doing before health stops us.
Mm-hmm.
I'm thinking like 2000 is probably
where
we're going to
That sounds about right.
Yeah.
Yeah. Yeah, I think that sounds right. So that'll be like another 25 years from now.
Yeah.
I'll be 7. Hold on. I'm 53 now. So I will be in my late 70s.
Yeah.
That seems about right.
Yeah.
Yeah. Yeah.
Things I think about while untangling my hair.
Well, we're building our house right now.
Yeah.
And it's all about no stairs. Like, what will be a house for old people? That's the house we're building. While I'm, working on increasing my deadlift and running up a mountain as quickly as I can in like some of the best health of my life, I'm like, this will not last.
Whereas us with our 4-story house, because we have a partially finished basement and a partially finished attic,
yeah.
I'm like, where can we put an elevator? Because
Right.
they have these really cool ones that you can get for $15,000, which is a lot of money. But if it allows us to stay in this house, because I do not want to ever move the contents of this house. Like, I want to die in place, have someone Gilbert Grape the house, just move on from there. Yeah.
Yeah, not me. I know we're preparing for this already. So yeah. All right, let's get started. Let me know when you're ready.
I am pressing record and pressing record. We are recording.
I have also pressed record. Here we go. Astronomy Cast, episode 750, the Supernova Early Warning System. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me, as always, is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. Happy 750th episode, Fraser.
This is it, 750 episodes, and we are going to celebrate by producing an episode of Astronomy Cast.
Which is like science. We need science.
That's just what we do. That's why we're here. So when enormous stars detonate as supernovae, they release a burst of neutrinos that can be the first sign of a coming explosion. Now, astronomers have built a network to watch for that flash of neutrinos and help direct their telescopes for when the sky show begins. And we will talk about it in a second, but it's time for a break. And we're back. So before we get into all of the really cool science and the network itself, and I think people are going to go, wait, what? You see the neutrinos before you see the light from the supernova. That's weird. I thought neutrinos nothing moves faster than the speed of light. The supernova is moving at the speed of light. How do we see the neutrinos first?
So neutrinos do move slower than the speed of light. They do have mass. They are moving exceedingly fast. Like, it took us forever, it felt like, to figure out if they had mass or if they didn't, because their speed was close enough to the speed of light that it was within error. We're talking about neutrinos from galactic or near galactic supernovae, so like the Large and Small Magellanic Cloud, close enough. And because
or in the galaxy, right?
Yeah, so galactic supernovae or near galactic.
Right.
And because there's a several hours lag between the neutrinos coming out and the first detection of light, that allows something moving near the speed of light to reach us before the light does.
Right, but why?
Oh,
like how
sorry.
How do we see the neutrinos before we see the light? If we saw Betelgeuse go off and it's only, say, 640 light years away, we would get the neutrinos before we saw the light from the supernova.
It all has to do with the fact that the neutrinos are just going to fly through everything for the most part. Some will interact. Whereas it takes time for the outer parts of the star to, first of all, figure out they're supposed to be glowing differently. And second of all, for that light from inner parts of the star to escape through all that medium where it's going to get absorbed and re-emitted and absorbed and re-emitted, and you get a lot of Brownian motion going on.
Right. I mean, we talk about this idea of this random walk that photons have to make to even get out of the sun in the first place. That when you have fusion at the core of the sun and it produces a photon of gamma radiation, that then that gets absorbed by another atom, and then that has to re-emit it, and then that gets absorbed, re-emitted, absorbed, and it can take 100,000 years from when a photon is generated at the center of the sun to when it actually reaches the surface, having been, now is it the same photon, it's been absorbed, re-emitted, and so on, but that's the gist of the dilemma. But a neutrino, I mean, we've talked about this, they'll go through a light year of solid lead, no problem. The interior of a star is nothing. It is like glass, light shining through glass to them.
And the time scales for all of this happening is kind of wild. You end up with supernovae happening in a couple of different scenarios where the core of the star suddenly becomes degenerate. Lead is the one that we talk about most, where you have a massive star that is undergoing nuclear reactions. It gets to the point where the core is built up into lead, and it goes...
iron?
That's what I meant to say, iron, Fe.
Okay.
I will forever remember the chemical reaction and not the name.
Say that again?
Yes, I'm going to say that again as I sit here horrified at myself. Thank you, Rich. Thank you. The one that we talk about most is iron. The center of the star builds up into heavier and heavier atoms. It gets to the point where it has Fe, iron, in the core, and it goes to try and fuse two of these atoms together, and the atoms go, hi, we need to have energy added to us if you would like to do that. Everything that's lighter mass, you go to add them together and they release energy. It's at Fe, it's at iron, where we have this sudden switch to the binding energy of the larger atom is going to need to have energy added into it. So
it's so shocking to me how instantaneously this happens, that up until iron, you did to me, up until iron, you've got this outward light pressure that's coming from the interior of the star that's pushing back against all of the mass that is trying to pull itself together. And you have this balance, this hydrostatic equilibrium. And as it moves up that chain of elements, you reach that point where you get to iron, and it's like a light switch. It just shuts off the entire star in a fraction of a second. And now suddenly there is no outward pressure, and the whole star just collapses inward. And there was like, it can get up to like 70% the speed of light. It is falling into the very center of this star. It's ludicrous.
One of the calculations I ran across while prepping for the show was the 5,000 kilometer across core that is iron will collapse down to about 20 kilometer across neutron degeneracy pressure supported neutron star.
Right.
In like 1 second.
1 second. Yeah, just boom. And all of that material is hammering the core to make that collapse, and that you get neutrinos from the highest energy reactions in the cosmos. And so you get an enormous amount of neutrinos that are formed in this moment, and they instantly escape while, as you said, the light and the matter is trying to figure out what to do. Like, do I move over here? Do you go over there? What's going on here? And finally, you get this flash of radiation on the surface of this star that then continues to glow and grow, and you get brighter and brighter and brighter. But the neutrinos are already gone.
Yeah, and the neutrinos are like every flavor, every style. The number of ways that neutrinos are getting created is kind of crazy. So first of all, you have, as the core collapses, you have the protons and the neutrons going, eek, eek. So the protons with the electrons are combining. They are producing neutrons and anti-neutrinos. Then you also have some of the protons and electrons are liberating themselves because neutrons are not stable. So you have beta decay and inverse beta decay producing electron neutrinos and antimatter electron neutrinos via both these mechanisms. Now, the creating the neutron core is the easy one to think about, but you also do have the neutrons that are going back into protons and electrons periodically. Then you also have all the thermal radiation that's coming out, where you have a ton of positrons and a ton of electrons that are going to annihilate against each other, producing light, producing neutrinos. So you have particle annihilation, which is a thermal production. We still don't have any evidence of it, but there's also theoretical concepts that photons interacting with particles could also produce neutrinos. It's wild, all the different things that are spontaneously going on, all because the center of the star gave up the ghost of potential energy, and it's something like 99% of the gravitational potential energy of the star gets converted into neutrinos.
So we're now going to talk about the supernova network, but it's time for another break. And we're back. All right, so we understand the underlying science that we get this cool trick that we can observe forthcoming supernovae. So what is the Supernova Early Warning Network?
It is a network of a variety of different neutrino detectors that work in a variety of different mechanisms, from water to scintillation fluid to you can actually have these things that use lead. This is where it's actually lead. And all these different methods of detecting neutrinos at all these different sites around the world are all unified in a collaborative agreement to share data. And if they suddenly get a flux of neutrinos, and we've seen this before with Supernova 1987A, we have seen neutrinos from other things like neutron-star mergers. They're there, and if they all detect these, they should have slight timing variations. And these slight timing variations are because of the path difference to each of these different places in three-dimensional space on the planet Earth. And if you have enough different places with enough accurate clocks, you can figure out where on the sky to point your telescopes. And because the neutrinos are coming out significantly hours before the photons should be detectable, there is a chance that we will be able to see a star from moment zero of light being given off.
And this is a big unsolved mystery in astronomy, that we catch supernovae after they've happened. Now, there are the occasional fortunate survey where someone surveyed a chunk of the space, and then one of those stars detonated as a supernova months or years later, and then they come back around and they're able to compare and like, oh, it was this star and then it detonated as a supernova. But nobody has seen those first moments, the initial brightening, the initial flash of radiation that happens in whichever order it does. That has never been seen before. And so the hope is on the Supernova Warning Network. Now, we know that we got that flash of neutrinos coming from Supernova 1987A, but we didn't have the warning network, right? Like, it was something they puzzled out long after the actual supernova had been visible in the telescopes. It was like, we see an increased amount of flux here. Oh, that was coming from the supernova.
And let's face it, back in 1987, neutrino detections were still new. This was still new science. We only had a few detectors in the world. Now we have more like dozen-ish detectors in the world. And by having more understanding, we now know that they switch identities neutrinos aren't big on staying who they're born as. So they'll switch flavors between electron, muon, all these different varieties. They do stay either matter or antimatter. That is locked in stone. You also have just all these different ways that we detect them again. So this is allowing us to start to see them at a variety of different energies. We weren't there yet in 1987. Now we're there.
Mm-hmm, mm-hmm. And so how many neutrino events, how many supernova has the warning network detected?
0.
None. It's found none.
Our galaxy is being super annoying.
Yeah.
So it's anticipated that a galaxy like ours should have somewhere between 0.8 supernovae, which really means 1 every 2 to 3 years, 0.8 supernovae a year, and 3 supernovae a year.
Isn't it per century?
That's what I meant, per century.
You want to say that again?
Sorry. Yes, I'm just going to say all the wrong things today.
It's fine, I'm here. I got you back.
Okay, thank you. It is anticipated that a galaxy like ours will have a supernova about every century. So it's not quite 1 per century. That's what you'll find commonly written. It's actually more like 0.8, which means 1 every couple of years, to 3 a century. So between 0.8 a century, or every couple of centuries, and 3 a century, we should be detecting these things.
But when was the last bright supernova that we saw in the galaxy?
Kepler?
Was it Tycho's?
Good Lord.
16... Hold on.
Tycho's supernova was...
1572.
And when was Kepler's supernova? 1604. Ah, I had it. Okay.
You did it.
I did.
Okay.
That time it was me.
But we'll talk about both of them then.
Okay. So, Kepler supernova, 1604, was the most recent. 1604 is more than 400 years ago. So
they're behind schedule.
Yeah. And so here's the thing. If a supernova goes off in a super dusty region, we may not see it. The neutrinos will be released. So we're now in a position to see things we couldn't see before.
I mean, like the other side of the Milky Way.
Yeah, exactly.
Yeah.
A lot of these star-forming regions, super dense with dust. Supernovas occur in star-forming regions. So there is a chance there have been supernovae that we simply haven't been able to see because they were obscured by all of the dust in the disk of our galaxy.
All right, we're going to talk about what would theoretically, hypothetically happen if there is a detection made, but it's time for another break. And we're back. Okay, so let's imagine that we do get a flash of a supernova. Something goes off in our vicinity. Maybe not Betelgeuse close, but 10,000 light years close. Play this out for me. What'll happen?
So what we expect to happen is there will be a wave of neutrinos that hit our planet passing through the planet. The detector that is closest to this incoming wave on our spherical world will detect the neutrinos first. As that wave passes through the planet, hitting each of the neutrino detectors on our world as it goes through, detectors will have signals. This will allow us to figure out the timing, if everything works and all the atomic clocks are properly synced and everything else. This will allow us to figure out where on the sky to point. Now, hopefully, in an ideal universe, that side is in darkness, and all of the detectors on that part of the planet point that direction.
I didn't even think about that. You've got like a 50-50 shot about whether or not it's going to be daytime or nighttime, and so then you're going to have to depend on the space telescopes.
And what's even worse is if it's within 30 degrees of the sun, we can't even point the space telescopes there because it will blast them.
And that's crazy. You could get a flash of neutrinos that are from a supernova that goes off on the other side of the sun. It would go right through the sun, no problem. Right through the Earth, no problem. And we would detect it, but we can't look at it.
Yeah.
I don't know, maybe like a mission like New Horizons or something that's in a different perspective could take a shot of the supernova, but that would not compare to the combined light gathering capacity of the Earth's and space telescopes that we have arrayed around our planet. That would suck.
Yeah. So there is that issue. Now, assuming that it occurs in a part of the sky where we can observe it, we get all of the most important at this point are the highly sensitive wide-angle cameras, because we're not going to, with a timing method, have it down to the tiny, tiny sliver of the sky that something like Hubble is able to look at. So we're going to need to look with the wider angle cameras. Luckily, we're starting to get more and more space-based wider angle cameras. Now,
like Euclid or upcoming Nancy Grace Roman or things like that.
Sphere, things like that. Yeah. So you look with the wider angle cameras. Software says, hey, this bright thing didn't used to be here. Study, study, study. The key things that we're going to be looking for are the evolution of emission lines. The thing that generates the light in supernovae that creates that wild light curve that we're so used to seeing is the radioactive decay of a variety of different elements. So as you get these different transitions, this is where nickel is one of the great blames for supernovae light curves, for instance. This allows us to see the emission lines, and it allows us to see the shockwave illuminated over a period of days and weeks. Now,
go ahead.
Now, there are two scenarios that are possible that will be very interesting. One of them scientifically interesting, the other oh shoot, this will allow us to explain the lack of observations for 300 years. So assume that something like this goes off, night side of the planet, everything's looking, nothing is seen. This will allow us to say this most closely aligns with these star-forming regions, all of which have massive amounts of dust and place a limiting magnitude of, if it was in these magnitude ranges, we wouldn't have seen it. So that starts to tell us, didn't see it. Now, the other thing that could happen is it's theorized that you can have core collapse without having a visible supernovae. Now, if you have core collapse without a visible supernovae, that means you look and there's no light, but you do get the neutrinos. So
like an unknown, like a star just disappearing, collapsing in on itself, and it not being able to create the supernova. And that's interesting. I mean, we've seen examples of stars just disappearing from the sky. And it's been thought that maybe that's what's going on, that it was there and then it imploded and it was very efficient and it ate the entire plate, right? And just collapsed it all into a black hole, which is mind-blowing. And then that would explain why we haven't seen the supernova, maybe. But as you say, there would be this flash of neutrinos, even though, and so that would be even more sign that we detect the flash of neutrinos, we look in the direction where it supposedly came from, and there's nothing there.
Yeah, so that's super interesting.
Yeah, and then the surveys show that there's a star missing.
That would be
great.
Ideal. Now, the probability of something like that happening is fairly low. This is not one of the common forms of things happening that we expect. But these are all the possibilities that the supernova early warning system is looking for. And they have a really cool network. It is funded by multiple funding agencies across the planet. This is international. It engages amateurs through the American Association of Variable Star Observers, which is not just Americans. It was just named over 100 years ago. And so there's people out there ready for these neutrinos to be detected, ready to point in the correct swath of the sky. This is kind of like the gamma ray burst alert network that we had in the early 2000s, when we were still trying to catch optical afterglows of gamma ray bursts for the first time. I mean, we'd seen them for the first time, but for like common times. Now, gamma ray afterglow is just like another day at the office, and it's the neutrino afterglows that we are chasing with fervor.
Yeah, yeah. And so hopefully the next time that bright supernova, that nearby supernova goes off in the Milky Way, we will be ready. And the Supernova Early Warning Network is the first step.
Yeah.
There are other plans in the works. I've reported on this, that they're looking to build more powerful versions of this, more sensitive versions that you could expand outward. And the goal would be to encapsulate Andromeda and Triangulum and try to bring more galaxies into this network. And that, theoretically, galaxies that we see within tens of millions of light years are giving off supernova. And eventually we'll get to this place where we'll see them every couple of years and we will have the ability to watch them as they unfold. But nothing would be as powerful as seeing one that goes off, Betelgeuse distance.
Yeah, and it's all about increasing the sensitivity of these systems. When a supernova goes off, all those neutrinos they go off in all directions, assuming symmetrical supernova. You have to do that sometimes. And so the further away something is, the smaller the cone of that sphere of neutrinos we're going to be able to detect. By increasing the sensitivity of our neutrino detectors, we start to be able to see supernovae going off further away. We start to be able to tap into the cosmological background neutrino flux. There's so much cool science to come out of this.
Yeah.
And I'm here for it, and we will be here for it for...
Totally.
Yeah.
Hopefully, I can't wait to report on the first detection with the network. All right, thanks, Pamela.
Thank you, Fraser, and thank you to all of our patrons out there who have been there with us over and over through the years. My browser signed me out while we were recording. So apparently, Rich, this is the episode we torture you in. Patrons, you are paying for us to torture Rich. Thank you. Thank you. You allow us to do good by him. Okay, I am now signed back in. Thank goodness for passkeys. All right, this week I would like to thank David Resetter, Travis C. Porco, Mike Husey, Jonathan Poe, R.B. Bask, Jimmy Drake, Bob Crail, Tricor, Noah Albertson, Ryan Amari, Mike Dogg, Simeon Torfison, Mark Schneider, Michael Purcell, Jeanette Wink, Brian Cagle, Jason Kwong, Tiffany Rogers, Robert Plasmo, Laura Kettleson. Red Bar is watching. A pronounceable name. You're welcome, Doctor. Jeremy Kerwin, Kinsaya Panflenko, Sherisum, The Lonely Sand Person, Scott Briggs, Benjamin Carrier, Jim Scholar, Marco Rossi, Nyla, David Green, Smansky, Rando, Benjamin Mueller, Benjamin Davies, Planetard, John Drake, Bruce Amazine, Paul L. Hayden, Jeff Hornmurder, Pauline Middlelink, Jordan Turner, Robert Hundell, Taz Tooley, Lee Harborn. Thank you all so very much.
Thanks, everyone, and we'll see you next week.
Bye-bye. And then they saved.
Episode 750. That's crazy.
Yeah. Your kids are so big now.
I know. Yeah. 22 and 20. No, 21 and 23.
Trillo over on Twitch says, as soon as we take things down for maintenance, probably 6 will pop in a 24-hour period.
Yes. Yeah, exactly. Okay. Load mine. Oh, why?
Doc Nappers is encouraging version 1.3 of our robot bodies to allow more episodes.
Yeah. Yeah, I will make that trade for you. So Alan Gross is asking, what is there a story to be told about what happened to the open space Q&A this morning? So I did it. I did it at 10 o'clock p.m. Pacific Daylight Time, Sunday night, which corresponds to 5 p.m. ish in Australia. And so I do three different versions of my live show to now. One twice a month I do it at 5 p.m. Pacific time, which is my local time, which would be tonight, but I do it once a month. I do it at 8 a.m. Pacific time, which corresponds to early evening in Europe and the UK. And then once a month, I do it on 10 p.m. Pacific time Sunday night, which corresponds to early evening in Australia and Asia. And so, and it rotates. So it always goes Pacific time, Europe, Pacific time, Australia, Pacific time, Europe, Pacific time, Australia. And so, and sometimes I mess up the times. So I had it set for 8 p.m. last night, and then I changed it to 10 when I realized it was the right time.
Daylight savings time is so deeply confusing.
Yeah. Like I can't wait till we're done and rid of it, because some people recognize it, other people don't, whatever. But the point is just to try and spread to make the time convenient around the world. And so that's why I do this. And I understand that it is like I'm always torn, because on the one hand, I get an entirely new audience. People are like, oh, finally, this is the first time I was able to attend one of these live, and they get to have their questions answered. And it's entirely new faces and names that I've never seen before, and I'm able to answer their questions. But also, we like a regular schedule.
Yeah,
we like to know if it's 5 o'clock, it's time to watch the show. Wait a minute, where's the show? How come it didn't happen? So there's a couple things to do. Like if it is important to you to be there for it when it's happening live, I will make the next event available on my channel the moment I finish the current the current event. So you can then man.
While you drink, I want to say welcome raiders to the people raiding over on Twitch. You have come to the Q&A portion of a live recording of Astronomy Cast. This is our 750th episode. We are here for your astronomy pleasure.
So you will get the notification when it's about to happen. That will come by email. It'll be a notification that'll pop up in your, but you want to be subscribed to the channel, and you want to click on the notifications bell. And then you'll see when the next one is happening. Put it into your calendar. Like if it's important, put it into your calendar. So the next one is going to be 5 p.m. Pacific time, Pacific Daylight Time, Monday, what is it? The 7th? The 7th. And then after that, it's going to be Monday the 14th at 8 a.m. And I'll move it right now. 8 a.m. Pacific time, which corresponds to early evening. So I don't know the answer to this. We live on a spherical planet, and it's really hard to be able to provide content to other people. Man, that 10 o'clock at night stream is hard for me to do. The 10 a.m. one or the 8 a.m. one, I am good to go.
Oh, I would be exactly the opposite. I know better than unless there's a really cool launch going on. I'm not going to stream before 10 a.m. local. The world does not need to see that.
Right. No, I will. Like I'm up at 4 usually, 4:30 in the morning. So
I will occasionally see 4 a.m., but it's from the other end, and it's because books are my problem child. I like to read too much.
No, I've finally really gotten my sleep schedule under control, where I go to bed at 9 o'clock, no matter what. And I used to be like, I take my Steam Deck, I take my computer, I'd plink away for a little bit. Now what I'll do is I'll be like, oh, there's a thing I want to research, a thing I want to work on, a game I want to play. I'll do that in the morning. Like if I get up in the morning, I still feel like it, then and of course I'm over it. Like, the problems are solved. I don't really care anymore. I get up in the morning, I work out, I eat breakfast, I start work, it all goes really well. So yeah, it's a funny thing to finally, like, I just finally recognized my pattern. Because the problem is, like, my brain wants to wake me up around 4 to 5 in the morning every single day, no matter what time I go to bed. So I have to go to bed at 9 o'clock to make that be 7 to 8 hours of sleep. And yeah, my wife just does not comprehend it.
I need you to teach me to use that telescope that when you're asleep.
Yeah,
I'm not.
I had all kinds of technical challenges with it, so that's a whole other conversation. Okay, so we got a bunch of questions about space and/or astronomy. Hal McKinney. So this is Hal McKinney's episode, and he wanted us to answer a bunch of questions about. Wanted to do an episode on neutrinos, and so this was the one that I've been thinking about. And so Hal McKinney asked, I think, 10 questions about neutrinos in this episode. So let's go with one of them.
Okay.
And if none of you jump in with other questions, this is just going to be Hal McKinney's questions about neutrinos. So please jump in with questions. But Hal asks, aren't neutrinos also a byproduct of high energy light waves? And if so, how do we know that the neutrinos we are detecting from a supernova aren't just a near Earth byproduct of the supernova light?
So it's theorized that we could get neutrinos from high energy light. That has not been detected. That is strictly theoretical. And it is something that would occur deep in the core of the supernova remnant as well, because you have this blast of radiation that's taken its own sweet time trying to escape from the core of the star that's collapsing. And if that's producing neutrinos, you will get different energy distributions from different events. Understanding the energy distribution of neutrinos is part of why we're so excited to have so many different neutrino detectors now. But yeah, we should be able to detect both, and both should precede the detection of light.
Yeah, I mean, I don't know of, like, if you have a gamma ray photon, that it will have to interact with a particle in a way that you could then get a neutrino released from that particle. But you're not just going to get a photon spontaneously producing a neutrino.
There is theory that that is possible. There is no evidence that it has ever happened.
Right. Okay. And even so, you wouldn't see you wouldn't see it in a directed area in the sky. Like, you would occasionally get these neutrinos coming from nowhere.
Again, this is the kind of thing where you're expecting it to come from these high explosive, high thermal areas. And so even if that is a cause, it's going to be coming from something like a supernova.
Yep. Francisco Sains asks, how far do you need to be for neutrinos and light to catch up? That's a great question.
So I thought about calculating that, and I regret that I didn't, but I didn't.
Yeah. That sounds like a ChatGPT 03 model type question where it'll do the math on that. So.
And it's further away than what we're able to currently detect based on sensitivity of, like, we detect a certain percentage of the incident neutrinos, and the number of incident neutrinos goes down as supernova moves further away, and we just don't detect them. So yeah.
Maura Labringi. I acquired a used telescope with a go-to mount. Do you have a recommendation for a good introductory book to get started in observation, including ways to set it up? I think that's sort of two separate questions.
Yeah.
Setting up an older go-to telescope is an acquired taste.
Cloudy Nights forums. That's where I would go. It's Cloudy Nights
that sounds
forums.
Great.
Yeah.
And probably ChatGPT. Like, I would probably explain your situation, provide the exact model, let it know about the software. It's going to recommend any ideas that people have to
this
make it better.
This is something where I think ChatGPT will lie to you. So go to Cloudy Night forums as well.
Yep. But in terms of, like, knowing what to target, I have two recommendations. One is there's a great website called Telescopius.
Yeah.
And it is a amazing resource that has all of the interesting things in the night sky in this giant database. You let it know where you are, and then it recommends the stuff that's going to be best to see tonight. And you can filter it in all these different ways. You know, brightness, location, distance from the moon, rising time, and it gives you these little graphs to show you when they're going to be visible and give you this really great sort of list of things. And with the go-to telescope, you just punch in the thing and then it will find it because you've polar aligned it. And now it knows how to find these objects in the sky. And so that's great. But that disconnects you from knowing where these things are in the sky. Yeah. And so the other thing that I recommend is a book called Night Watch. And that's what I learned for finding objects in the sky when I was 14 years old.
I found my copy this weekend while cleaning.
Great. Yeah, they keep producing new versions of Night Watch. And it has this, opens up nicely, beautiful maps of the night sky. You find the object that you're looking for. It shows you how to star hop to find them. And so that you can do without using the go-to, just learning to find these things on your own. It's a deep hobby. And so give it time. And I would say that mount may vex you.
Yeah, I have to admit, I have one go-to mount that vexes me. So I just pull out the lack of go-to mount periodically. Exactly. But I have another book to recommend. Yep. The Royal Astronomical Society of Canada puts out a calendar every year book that lists everything by season, by constellation. It has a section of globular clusters, there's a section of nebulae, it has a section of Messier objects, it tells you what planets are when. This is a book that if you have the money, and they're like 20-something bucks now, I think, buy one every single year. And even if you don't do that, an old one, it's not like things stop being up in September other than the planets. So the globular clusters are going to be the same year to year, planetary nebula. I love this.
It's a great book.
I've relied on it since I was a baby astronomer.
Yeah.
It's brilliant.
Like occultations, meteor shower peaks, all of the transits, all of the eclipses, it's all listed. Potential interesting comets that are expected to come by. Yeah, that's a good one.
So Sishu over on Twitch asks, what is the theory regarding neutrinos changing flavor? So it's just one of those things that they do. They will actually switch They will switch mass and velocity ever so slightly, so they're conserving the two. So kinetic energy plus potential energy plus mass energy will stay constant. Exactly what the neutrino is will change, and this was ultimately the explanation for the solar neutrino deficit. And what's cool is they've done crazy experiments where they've had a neutrino detector in one place, they've had a source of neutrinos in another, and they've looked to see how many identities changed between the two places.
Very cool. Do you have any more questions over on Twitch?
Is the book on Amazon? I don't know, but Keeper of Maps posted a link to it on the RASC website.
Oh, there you go. Yeah, so rasc.ca/handbook.
Yeah.
Yeah, and our tamed amateur astronomer, Dave Dickinson, he recommends it as well. Did you just
call him totally tamed?
Our tamed, he's our tamed amateur astronomer.
Are most
the one that we have on staff.
Feral?
Yes.
Okay.
Yeah.
Okay.
That is a reference to Top Gear. They have a tamed racing driver who tests all of their different cars on the racetrack. So
I like this. I did not know this. I appreciate this.
Yeah. So they're feral, and we've been able to convince one to discuss amateur astronomy on Universe Today. But yeah, the Observer's Handbook, good stuff. I should interview them. It's a good idea. I'm gonna do that. What else you got?
Assuming a supernova happened in the right safe location to view, how long to crash code and repoint a space telescope?
About 3 hours.
Yeah. And it turns out that there is a long known and understood process for alerting that something has happened and automatically interrupting an ongoing observational program. It's actually crankier when you're dealing with real astronomers. I have gotten the 5 a.m. there's been a gamma ray burst, please repoint the telescope phone call and be like, grr, okay, I'm going to do this. Grr. Most telescopes now are Q-based, so you may not have a astronomer there in person. They're not most Q-based. They're most either Q-based or night assistant, and the night assistant is going to do what they're supposed to be doing, but they might get yelled at by a human. Right. So space telescopes, super easy. It's already a known solved problem of if this, then that on next exposure.
Yeah, I mean, it's a great idea that the astronomical community understands that there are events that are so important, so important scientifically, that it's okay to interrupt the work that's being done. And so many astronomers they've put in their proposal, they've received time on the Hubble Space Telescope. They know exactly when they're going to be getting this time, and then just before their observation, something really important happens, and Hubble's like, sorry, busy, gotta go check this out. And then they have to get put back into the queue at a later time. And it doesn't happen very often, but it does happen. And the most classic example of this was the Kilonova event that happened back in 2017.
Every observatory in the world was like, we shall look at this.
Yeah, exactly. That there was no chance that you were going to complete your observations during that night, that every telescope was then watching fiendishly for hours and hours and hours
and somehow
to catch
they all
the afterglow.
Kept it secret. That's the thing that still floors me.
Yeah, me too. Yeah. What else you got?
Feral amateur astronomer, be careful in nights with a full moon. I appreciate that. I'm not seeing any other questions, just beautiful snark.
All right. So Helen Kinney asks, since neutrinos are the smallest known particle with mass, how do we know that they're not the constituent particle of all other particles in the universe? I mean, that's quarks, right? Yeah,
that's quarks. And I mean, we get down to what's a lepton, what's a boson. There's different classes of particles. Some particles are fundamental, some aren't. Neutrinos do not add up with their different spin, charge, things like that to be other particles.
Right. They are a rounding error.
Yeah, that's exactly what they are. When you have protons, electrons, and neutrons interacting, you end up with electron neutrinos. When you have similar families of muon interactions, you end up with muon neutrinos. There's a chart. Everything is related to the chart. Quarks are in there. It's literally a grid chart, and we were able to predict particles by what was missing in the grid. It's math. Quantum mechanics is really cool.
Hal McKinney asks, do you remember anything from episode number 1?
Yeah. I was in a hotel room. We were talking about the vote in Poland to demote Pluto, why Pluto doesn't fit in with the other planets, but how the definition still sucked.
Yeah. Yep. And it's kind of amazing. Like if you go back and listen to that episode, and I will never go back and listen to that episode or any of the episodes that we've ever created. I delete them. I don't even subscribe to Astronomy Cast.
I listen to them to add bookmarks to the YouTube videos sometimes.
Oh, do you?
Yeah.
No, I won't do it.
I just fill in for folks doing work periodically.
Right.
Yeah.
But if you do, you will find that it is really similar in cadence and conversation and mood and all of that kind of stuff. And it's funny, like I talk to my patrons and they talk about how they go back and listen to the early episodes of Astronomy Cast because, back then we had wide open territory that we were trying to fill in, the sun, Pluto, Jupiter, Jupiter's moons. And now the episodes are a lot more finely, we're filling in all the little missing pieces as we go and updating on all the new stuff that's happening. But we will never be able to do an episode called Black Holes again. And yet, I think we nailed the style and the concept and the theme from day one. And so we've still just been implementing and iterating ever since.
It's the technology that has changed and the fact that I had to get comfortable with doing video.
Right. Yeah. That was like 2012 when we started to do that as part of Google Plus.
Yeah.
But still, the actual conversation itself, the episodes itself, the length of them, the back and forth, the reliance on Pamela's deep knowledge, me being, Fraser Everyman.
So much since then. Like, you used to ask questions where I was like, oh no, he asked a pseudoscience question. Oh shit. I don't do that anymore. And now you catch it when I say stupid things.
Yeah. That's what do you know? You teaching me for 750 episodes has taught me things.
It's awesome.
So, I think that's what it's supposed to be about. And so it's funny because people say, oh, you should, have you ever thought about going back to university to get your astronomy degree? And I'm like, why bother? I got it. I was tutored by a PhD astronomer for 18 years. What more could I want? No. And then you match that, and then I do my homework, right? I do my assignments, and the two come together to create, currently. And absolutely. I think that, the biggest, people ask me this, they note this sort of progression from me not knowing and asking a lot of, stupid questions to me being a lot more of a producer / peer in the conversations that we have. But around, whenever you started doing daily space, your capability changed dramatically because very much you were specialized in the things that you really knew, but the rest of you didn't have this deep knowledge about. But once you started to report on the news and have to research into it and start to fold this stuff into your understanding, you became much more flexible in the kinds of topics that you could then provide a very deep explainer on. Because, how could you expect a galactic astronomer to know about perchlorates on Mars?
And
right?
Now I can talk about like why olivine matters, whereas at one point I had to hunt down Emily Lactawala and be like, why do I care about olivine?
Why do I care about this? Yeah, exactly. And have a lot of gaps in your knowledge. And so I think that me continuing to do the work that I do and you continuing to do the work you do has made for a much better show. And I think the hard part maybe now is for it to feel, us to maintain that theme and for it to feel very natural, where I'm still trying, I asked you a bunch of questions in this episode. I totally knew the answer.
Oh, I know.
Right? But I knew how I want a person who doesn't know what we're about to talk about to appreciate to feel it.
And it's made you such a good interviewer for everything you do over at Universe Today. And for all of you who rated on Twitch and are new to this, Fraser's you're over there on screen. Fraser is the producer of universetoday.com. I'm the director of cosmoquest.org and host the Escape Velocity Space News show that used to be the Daily Space, and then realized Daily was not going to allow me to keep doing research. Plagueis, thank you for the subs. We live and breathe space news, and you are, I think, the best interviewer in our sector, and you just do super cool stuff. And I don't know how you get all the people you get. It's just amazing.
Oh, that's easy. That's easy. Okay, just ask.
But just hunting down emails is hard sometimes.
Yes, that part can be tough.
Yeah.
So here's the trick. There's two tricks. One trick is if they've got something to promote, like they've just written a book, then they're in this mode where they're looking to communicate it. But I'm less interested in those people now. That used to be compelling to me, but now I don't, less interested. But it's the when they work for some larger agency like NASA or a university or whatever, then I can lean on the press office and go, can you please give me somebody to interview about the Titan Dragonfly mission? And they'll hem and they'll haw and they'll find a person and they'll want to sit in on the interview. Is this the right person? And and then I can just be insistent. Like, you have one job
Yeah.
to promote the work that you're doing. We are a trusted outlet for that. Do your job and get me that person. And they get me that person every time. Never fails.
That is excellent.
Yeah. Yeah. So just these people exist. Press officers exist. They have the names. They have the Rolodexes. They can get people within the organization to do the interview. And so it's just a matter of helping them, encouraging them, allowing them to do their job. So no, it's amazing. Like, yeah, Neil deGrasse Tyson is busy. Brian Cox is busy. Michio Kaku is busy.
And they're not actively doing research.
And they're not doing research. So they're actually super not interesting to me. Like, if you said, you could do an interview with Neil deGrasse Tyson, I'd be like, no. What else you got? Who else you got? Right? And it's not like, he's terrific and the things he says are wonderful. And I really enjoy listening to him talk. But I want the person who has their head down, has been doing the research, is not an experienced communicator.
You actually want the postdoc in the team.
I want the postdoc. Yeah, I don't even want the professor who has taught the postdocs. I want the postdocs, because they are absolutely cutting edge and current. And if they've been raised in a nurturing environment, then their professor is going to be glad to get out of the way and let them showcase their work. And this is a thing that I figured out over time, is just ignore, go for first author, ignore the luminary that's on the paper, go for the person who did the hard work and is also going to be really fun and interesting to talk to.
So one of the folks over on Twitter didn't quite catch Michio Kaku's name when you said it and turned them into Pikachu. And
I would love to interview Pikachu.
Yeah.
All right, we've reached the end of our hour, so it's time for us to wrap things up. Thank you in advance to all of the people who are going to have to deal with the nonsense that we have just dropped onto their server.
So
much nonsense. This is all on you. Have fun with this. Pamela, thanks as always for being my partner for 750 episodes. And here is to 750 more. And we will see all of you next week. Thanks, everyone.
Bye, everyone.